Hello and welcome to my YouTube channel. Today I'm going to be talking about network reduction method, but I will be talking about other methods in the subsequent videos. So after this video, you watch out for the other videos on the other methods that we have already discussed during lectures. Now, when it comes to network reduction method, it's based on the idea that if you have a complex network, right? A network here just means a circuit diagram. So you have a circuit diagram whereby you have a connection of resistors in series or in parallel or a mixture of both, right? Series and parallel connections. You can actually reduce that to a simple circuit whereby you have a voltage and then a series with a resistor. And this idea is just based on what? Ohm's law, which says that the current passing through a resistor or a conductor in a circuit is actually proportional to the voltage supply. So we have current being equals to what? Voltage over resistance. So anytime you have a complex circuit diagram whereby you have connection of resistors in series or in parallel or a mixture of both series and parallel connection, then we can reduce that circuit diagram to just a voltage in series one resistor, one voltage and one resistance being the equivalent resistance. So we have an example here. You can see here we have R1 and R2, they are connected in series. So we can calculate the equivalent resistance because the same current is passing through R1 and R2. The current there is I. So we can calculate the equivalent resistance. That will just be the sum. That is R1 equals to our equivalent resistance equals to R1 plus R2. Now, once we have done that, you can see that you can have a simplified circuit whereby you just have a voltage supply. Then we have our equivalent resistance. So from there, we can get the current as usual, and the current will be equals to voltage over the equivalent resistance. So we have this. I'll be talking about other examples as we move on. And in this example, you can see that we have two resistors. This time they are connected in parallel. Right. Now, here again, when it comes to applying network reduction method, we are trying to reduce this circuit diagram here so that we have just a voltage and then an equivalent resistance so that we can then apply Ohm's law. So based on this, we calculate the equivalent resistance for these two resistors connected in parallel, and that is going to be equal to, since they are just two resistors, that is going to be the product over the sum. So R1 times R2 over R1 plus R2. Or you can come and use the formula, which is 1 over equivalent resistance equals to 1 over R1 plus 1 over R2. That will give you the equivalent resistance as well. Once we are done, then we come and apply Ohm's law. We have now equivalent circuit. So we have Ohm's law, voltage over the equivalent resistance. And that will give us I, which is the current, that's the main current, or we call it the total current. Why? Because if you look well, you can see that this current comes to the node. Here's a node because here is a point where three components are connected. So it's a node. Then after this node, then it gets divided. So you can see I is entering after then enters the node, then it gets divided. So we can find I1 and I2 by using current divider rule. So we come here, I1 will be equals to. So we are interested in the current passing through R1. So we block that very resistor. Then we take the other resistor, which is R2 over the sum of the resistors connected in parallel. So you can see clearly it's what R1 and R2. So now we sum R1 plus R2 times the total current entering the node. That will give us I1 And then similarly, I2, if we are to calculate for I2, we have the current passing through R2, we block that very resistor, we take the other resistor, now with R1. Then over the sum of the resistor connected in one parallel, so we have R1 plus R2 times the total current. We get this network or circuit diagram so that we can have a simplified circuit whereby I have a voltage and then I have my equivalent resistance. Then I can calculate the current passing through the equivalent resistance. So how do we get this? Right? The equivalent resistance, that's what is important here. Here we can just calculate this straightforward by looking at the circuit diagram. You can see here R2 and R1 and R3 are connected in series. So we can do the equivalent resistance for those two, right? So that will give us R2 plus R3. So that is the sub-equivalent resistance. And then after that, this will be in parallel with what R4. So since they are going to be in parallel with R4, that means I'm going to take the product over the sum. So I have R2 plus R3 times R4, then over R2 plus R4. Then after all this, then this part will now going to be in series with R1. So we add plus R1. That will give us the equivalent resistance. And we refer to this as the overall equivalent resistance because we calculated some equivalent resistance for R2 and R3. Then after this, you get your total current or the main current being equals to voltage over the equivalent resistance. And then after this, you can get I1 and I2 by using current divider rule. Okay, we take a look at the last example. And this one, you have a situation whereby you are given a network, meaning a circuit diagram, and you have a voltage source, then you have connection of resistors. But this time, we have a situation whereby you cannot clearly see what series and parallel connection, right? So, for example, here, our main circuit, the resistors are R1, R2, R3, R4, R5, right? So for the time you forget about these other resistors inside the delta shape that you can see here, right? So if you look at focus, and then you can see that R1 and R2, they are not really in series because you have here, if the current comes, it gets divided. And then you look at R1 and R3 to the same thing. They are not connected in parallel. Why? Because if I have R1 connected here to, they are not then connected to each other. You have them going towards R2 and then to R1. So here, clearly, if you look at this circuit diagram, you cannot clearly see what series and parallel connection. So what we tend to do is that this is when we use network transformation. So you can see clearly that we have a delta shape for the top resistors, R1, R2, and R3, they form a delta shape. And then if you look at now, R2, R3, R4, they also form a delta. So we have two delta shapes here. Since we cannot clearly see series and parallel connection, we do network transformation. We insert a Y network into one of the delta networks. So I've selected the top one. That's why I have this here. Now after the insertion of that Y network, we have to calculate their parameters. So how do we calculate their parameters? I can get RA to be equals to what? RA is here. You can see that it's adjacent to R1 and R2. Those are delta network resistors. So now we equals what? The product R1 and R2 over the sum of what? The delta network resistance. So that'll be R1 plus R2 plus R3. And then we come here and do the same thing, calculate for RB. We come to RB, the product of what? The delta network resistors adjacent to RB, that will be R1 times R3, then over the sum of the delta network resistors. So we have R1 plus R2 plus R3. And then the last one, the same procedure, we have RC, the product of the delta network resistance adjacent to RC, that will be R2 by R3, and then over the sum of the delta network resistance. So once we are done, we now erase the delta network resistance because we have transformed it to now our one network. And once you do that, you get something of this nature. Now you can now clearly see that there's series and parallel connection here. You can see RB and R4, they are connected in series. The same for RC and what? R5, they are also connected in series. So we can calculate the equivalent resistance for those two parts. So I have this R1 plus R4, then the other one R1 plus R5. And you can see that after that, the resistors here, they are now going, they are what? In parallel, right? So if they are in parallel, meaning I can take the what? It's just a product over the sum. Then we have this, the product over the sum, that will give you this. And then after that, remember we have RA here. After that, it's going to be in series with what? RA. Then we add our RA. So that will give us the overall equivalent resistance. Then after that, we can now we now have a simplified circuit whereby we can use Ohm's law. We have our voltage and our equivalent resistance. So current here is going to be equals to voltage over the equivalent resistance. So make sure, if it's your first time watching this channel, make sure you subscribe, and I'll be uploading more videos on the other method. For example, I'm going to upload videos on Branch-Kern method, nodal analysis, mesh analysis, and source transformation. So make sure that you subscribe and then comment if you have any question. Bye-bye.